Good evening, everyone. Welcome for today's lecture. My talk today is about data, learning, and decision. When we talk about data, actually we consider in big data environment. We talk about the learning. It's about machine learning, which is an important part of artificial intelligence. We talk about the decision. It's how machine learning can learn from data to support decision making. In big data situation, data is in different forms. We have high-speed data, we have data streams, and we have multiple data sources. Machine learning actually is algorithms or models. Then how machine learning can learn from data to generate knowledge for what? Knowledge will be used to support prediction and decision making. So my talk today has 3 sections. One, about the data. We will talk about different forms of data, and we will identify the challenges in data. Section 2 is machine learning. We know machine learning has many different types of machine learning, from transfer learning, reinforcement learning, deep learning, many types, and subtypes. But today, we mainly talk about 3 types of machine learning to deal with the 3 challenges we identified in data. Section 3 will talk about decision making. In principle, we have 2 types of decision making. One, to support managers. Another is to support customers. So those are my talks today to deal with the 3 parts, but they are linked together. So section 1 is about the data. Data is a fundamental of machine learning. But why machine learning become very hot now? Why we have so many new types of machine learning algorithms, methods developed? The reason is clear. We have data available. We have large data sets available. We have big data available, which was not available 30 years ago. So my first talk is about data. And the data, we have structured data, unstructured data, we have collected data or data streams, and I will discuss all the details one by one. Database and the data warehouse. Database deals with structured data. All data we collected, put into database, build ER model, primary key, foreign key, and so on. Very structured. And in many industry applications, they have a data warehouse that's not 100% structured, could be semi-structured. But in big data situation, we have data streams, we have lots of data graphs. In that case, we have unstructured data. We cannot use the same methodology to deal with structured data and unstructured data. And from machine learning point of view, we have static data and streaming data. We do survey, questionnaire, we collect data, we put it into data set. Once finished, that's static data. But in many big data situation, data come as a stream, okay? Keep coming. Now in such case, we will have new challenges because we need to consider the data distribution keep the same or the data distribution keep changes. Then we need to deal with the changes for data distribution if they occur. labeled data and unlabeled data. That's so important for machine learning. That's how to deal with unstructured data is a challenge in machine learning. So, based on this above analysis about the data forms, we identified 3 challenges from machine learning point of view. 1, in-domain data insufficiency. 2, involving data distribution. 3, data uncertainty. Now I will discuss the 3 challenges from machine learning point of view in detail. Sometimes we have a new market or we have a new product. Then we want to have prediction about usage, about user behaviors, and so on. But we don't have enough label data to build a prediction model. However, we may realize in another domain, lots of data available. They can build any prediction models through machine learning. The 2 domains are similar. The idea is, can we use the knowledge learned from this domain with big available label data to transform to support prediction in a new domain which doesn't have enough label data for new product, for example. That is a data insufficiency problem, and later on we will discuss solutions. Challenge 2, about the changes of data distribution. Everyone will use the mobile phone for a number of years. Think about 6 or 7 years ago, you use your mobile phone. At that time, you only use your mobile phone to make phone calls. But 3 years ago, the usage is different. You use for phone call and you use to make a photo. Then you use to check the internet. Then you use for Google Map. And more recently you use for WeChat. What is the changes now? Now probably 30% of your mobile phone usage for internet search. Another 30% of your mobile phone usage to take photos. And 10% of usage for WeChat, about 10% for Google Map, and so on. Only 5% of the usage of your mobile phone to make phone calls. That's its usage distribution changes. In such case, if you still use data collected some years ago to build a usage model for prediction about customer behaviors for current situation, of course doesn't work. You cannot get high accurate this prediction. So we need to consider build new models when you have a new situation. That's challenge 2. Challenge 3, data uncertainty. Data uncertainty, including data value uncertainty. A lot of data we collected are in linguistic terms. They're very, very high, very fast, or about $1,000. Those are linguistic terms. And sometimes we have data missing. And sometimes when you consider data matching, all of those have an uncertainty problem. So now we identify the 3 challenges in data. We go to section 2 to talk about machine learning. We talk about the data forms, and we talk about the 3 challenges in data. And now we can see how machine learning can deal with the 3 challenges. So in my following talk, I will give you some ideas how transfer learning can handle challenge 1, data insufficiency. how concept drift learning can handle challenge 2 for data distribution drift, how machine learning, fuzzy machine learning can deal with data uncertainty. What is machine learning? Basically, machine learning is to discover some patterns from data, probably from pre-processed data. Then generate knowledge. When you have a new data, then you will use the knowledge generated from historical data to support decision making or prediction. Now we go through the 3 typical machine learning algorithms today, method, and to handle the 3 data challenges we identified. The first one is transfer learning. The idea of transfer learning is to borrow knowledge. You can say, we would like to have some prediction about zebras' behaviors, but we don't have enough label data. Data insufficient. However, in another domain, very similar domain, horses we have many label data. Can we use the knowledge learned here to support our prediction about previous zebras' behaviors? That is the idea of transfer learning, aimed to handle the challenge 1 in domain data insufficiency. Now we give you a basic concept of transfer learning. In transfer learning, you have a source domain. In the source domain, you have enough labeled data. So you can train a model and generate prediction. And here is the target domain. You would like to do classification or recreation, any prediction models here, but you don't have enough label data. So it's impossible to train a model. Now the idea is, how can we use knowledge learned here to support model establishment or to support outputs generation for the target domain? What is the issue? The issue is sometimes target domain's feature space is the same as source domain, but sometimes source domain's feature space is quite different from target domain. Sometimes you have some common features, sometimes even not. That is a challenge given to transfer learning. Here are 2 models, 2 algorithms we developed. The first one and second one, we all consider the situation source domain and target domain have same feature space. And the first one, what is the idea? The idea is we use the source domain to generate initial labels for target domain. Then we use the limited number of label data and source domain data to do label refinement. So in such case, source domain data will be used from beginning to the end, and for target domain, we only do label refinement. The second is different ideas. For source domain, we build knowledge. After knowledge is established, we don't use any data from source domain anymore. Then the knowledge could be described by models or rules. We do knowledge refinement, and finally we generate knowledge for target domain. This result has been published in attribute transaction fuzzy systems. Cross-domain transfer learning. Source domain and target domain have different feature spaces. Sometimes you have some common features, sometimes even no common features. We developed two strategies to deal with. The first one, from the common features, we put together, and then we built correlations between the common features and the other features, or common features and other features. Finally, we built correlations between two domains. The second one is quite different. We are going to build latent feature space and two mapping functions. So here is the source domain, here is the target domain. You don't have any common features. But we build a latent feature space. We try to find a mapping function for source domain mapping to the latent space. For target domain, also mapping to latent space. In the latent space, the two domains have same feature space so that we can do knowledge transfer. We are doing currently, this is fully supported by current ARC-DP. We have a number of source domains. And the target domain is one. How to transform knowledge from number of source domains to support prediction in target domain. And target domain sometimes need multiple outputs. So how to transform multiple source domains with multiple outputs to support target domain. So now we have mentioned a number of solutions to deal with challenge one. Now we go to second part, concept drift learning to deal with challenge two, that is data distribution challenge. We know this traditional machine learning has an assumption. That means your source domain, your past data and current new data have same data distribution. What is the main issue or the key technology is when is the best time to update a training model or update a learning model. That is the key. So in our team, we developed a number of technologies to deal with that. Before I go to the deep of concept drift learning, I need to mention there are four types of concept drift. One is sudden drift, second is gradual drift, and also incremental drift, and recursory drift. So whatever which this concept drift, we can use that framework to deal with, to describe the concept drift, how to identify and how to reaction. When you have a data stream, then you need to test any drift, yes or not. If say no drift, that's okay. You just use all the data, or you just use data established by the historical data. And if say yes, there is a drift, then you need to do drift understanding. What it means? That means where is the drift, when the drift occur, and how big the drift. That is the drift understanding. And after drift understanding, we need to do drift adaptation. So three important stages and important elements of the framework about learning and concept drift. One is drift detection, two, drift understanding, that's third, about drift adaptation. There are two big strategies to handle concept drift. One strategy is the lazy strategy. For lazy strategy, what do you mean lazy? That means always detect, then do reaction. Okay, so that is a lazy strategy. Under lazy strategy, still have three different sub-strategies. One is detection and retrain model. Second is detection and adjust model. Third is detection and don't adjust the model, but adjust prediction, the output. Second big strategy is the active strategy. What they are doing, incremental learning, don't do detection, directly learn. And there's another is example learning, and another is active learning. So my talk today focuses on this lazy strategy. We do detection. Under lazy strategy, there are two different methodologies. One is tracking the learning model performance. For example, this one you can see this accuracy, okay, this accuracy down, and accuracy down, and accuracy down. When accuracy down, that means a drift happened. The second strategy we use to sample text. So you can see this distribution example 1, that's distribution example 2. You can see the changes of the distribution. My talk today focuses on the second one, to sample test. And to do two sample tests, I need to mention one competence model developed by my team. That is sample 1 in time t, sample 2 in sample t plus 1. We want to say any drift happened between the two samples. What is the main idea? How to calculate? Impossible. So our idea is to transform this one sample into one vector. So we can calculate the distance between two vectors so that to identify the changes of data distribution between two samples. To do it, we combine this one mix together and we establish this related site and related cross site. And then we use this one, get data for the two vectors, then we calculate distance. So that is together is a competence model. This one published in Artificial Intelligence. So use the model. You only need to say the changes of competence model so that you can make this decision or identification of the changes of data distribution. That is drift detection. About drift understanding, we can consider where and how and when, but today we only talk about where. We know concept has a drift, but where is the drift region? So we developed a method published in pattern recognition that's to identify the very accurate drift region. Now, when you do detection understanding, the last one is drift adaptation. We use case-based reasoning as example. We use competence model, and we have this data stream, and as a new case come to case-based reasoning, come to case-based, then you need to maintain, aggregate your case base. But when you do this one, you need to meet one challenge, which is redundancy. We developed a new idea and a new algorithm for concept drift adaptation, and in this redundancy removal in this way. We removed this redundant data. However, we still keep that figure so that you can get that classification decision boundary, but more important, you also can keep knowledge. So this also published in Artificial Intelligence. The third machine learning part, we call fuzzy systems. We use fuzzy systems to handle uncertainty, to deal with the challenge 3. we have different types of uncertainty. For example, data value uncertainty, data measure, data relation, and data processing, data missing, output value, all may have uncertainties. We want to model uncertainty, we want to deal with uncertainty to achieve high prediction based results. So number of fuzzy models have been developed. For example, there's a fuzzy measure, fuzzy rules, fuzzy relation, and fuzzy classification, fuzzy clustering, and so on. We only mentioned some developed by MIT. So for fuzzy data input, if you only have a linguistic term, say very high, what is very high? You say young, he's young. What means exactly young? So we use membership functions to describe the fuzzy value input. Fuzzy measure. This one is used in fuzzy transfer learning. For one instance, we need to find 10 similar instances and 10 dissimilar instances. And how to find the similar one? What does it mean similar one? So we introduce the fuzzy set into the distance measure. Then we can find 10 fuzzy similarity one and 10 fuzzy dissimilarity one. Fuzzy clustering. We know we built knowledge. Knowledge can be described by rules. How to generate rules? Rules come from clusters. But for the clusters, we can say some is distance very close to the center and some far from center. In such case, we introduce fuzzy clustering and to consider the membership functions of each instance, how high or low belong to a cluster. And this also published in IEEE transaction fuzzy systems. So that's Solomon, we built fuzzy rules through fuzzy clustering, and there are the list of fuzzy rules as sample. Then, of course, we need to define 5 functions and optimize 5 functions, and finally we get fuzzy rules for target domain, and use fuzzy rules, we get the fuzzy clustering. That's fuzzy rules, so that we can generate prediction in target domain. This is also published in IEEE, this transaction fuzzy system. That's why information granularity. This is so important and a very good example. Everybody uses mobile phone at the moment. And our mobile phone now probably easily to have 128 GB as a memory. And if we want to transfer this knowledge, do transfer learning from data last year or last 2 years, at that time you don't have such big memory in your mobile phone. At that time, bigger, largest one, maybe 1 GB. Okay, then if you transfer 1 to 1, of course, not right. So what we need to do, we need to transfer 1 at that time is the largest to large memory, and to convert 128 to large memory, and the large memory transfer to large memory. That is information granularity, and that is very significant this part to use fuzzy systems. Now we finish the section 1, data, section 2, machine learning. We go to the last section, decision making. In data part, we identify the challenges, and in machine learning part, we developed a number of new machine learning algorithms to deal with those challenges. And now we need to think how machine learning algorithms can support prediction and decision making. In those parts, we need to mention decision support systems to support managers and recommender systems to support customers. decision support system, and we can mention three main types. One is a model-based, one is a data-driven, or we can learning-based, machine learning-based. Another is knowledge-based. This one is the recommender systems we developed, and here is the decision support systems we developed. What is the model of decision support systems? We first talk about decision support systems. Model-based. This is programming. You build programming, you find this method, you get the solution. Nothing about the machine learning. The second one, data-driven machine learning. Then we have a programming, but for the parameters, we need to use machine learning to generate. Then we get a method solution. The second situation, even we don't use this program, we just use data, directly go to machine learning, generate rules, for example, and find a solution. So in that case, we have machine learning to generate parameters, and the second is machine learning directly generate output. And also we have knowledge-based decision support. This is example about the model-based decision making. So Mike, you can say, we assume we have a number of these farms as a milk producer. And we have a milk transport company. They have many trucks. The trucks need to go to each farm to pick up milk. But we have lots of limitations. Number one, the milk must be picked up within 48 hours. Number two, milk must be cooling down to 4 degrees or less. You can pick up. Number three, for one particular farm of the milk, you pick up, you need to pick up all, then clean the container. They would like to minimize the cost of routing and make sure you collect all the milk. So this is a model-based decision making. For data-based decision making, we have two types. One, we need to build this optimization model, but all those parameters come from machine learning. The first one comes from experts. The second, we don't need to use any optimization model. We just use data, generate rules, and use rules to generate options decision support. Consider the second type. And what we need to do, you collect raw data, then you do pre-processing, then you have transfer the data, then you do machine learning, okay? Then you generate a result. So the impact of machine learning in decision making, we can list the four main parts. One is you can use this one. You can use, for example, concept drift detection to identify customer trends or to generate early warning systems. This is for data analytics. The second, you can use machine learning to support the business for continuous evaluation because you need to update your evaluation model on time. The third is real-time support for decision making. That's, for example, reinforcement learning. The last one we list here is about when you have a new product or new market, then you need transfer learning to deal with data insufficiency problem. Knowledge-based system, we can consider to use case-based reasoning and to build a knowledge base. And at the moment, some decision support systems combine knowledge base with machine learning together. so that you can learn rules built into knowledge and use knowledge compared with the business rules to support decision making. That is the decision making mainly support business and support managers. The final part, I would like to mention recommender systems. It is an important part of decision making, but they aim to support customers, support users. This, for example, that is recommender systems we developed for small and medium businesses to find partners. We call Smart BizSeeker. And in recommender systems, we have three main types: collaborative filtering, content-based, and knowledge-based. But today, I just quickly talk about collaborative filtering. Collaborative filtering is the more popular one. The main idea is they have a user item matrix. Every user, after you do online shopping, and you give a score. In such case, we can use the score to identify similar users. What does it mean? For example, you mark item 1 very high, I also mark very high. You mark item 2 very low, I also mark very low. So that means we have same preferences. We are similar users. We assume user 1 and user 2 are similar users, and being user 2 gave a high mark for a new item. I assume user 1 will love it as well. So that's the main idea of recommender systems. And here is the outcome of recommender systems. Just generate a recommendation about top 3, 1, 2, 3. But this one is the recommender system we developed for a telecom company. The users, not a single user, is a small and medium business. And so every recommendation is a package. Recommender systems has and still has some data problems, challenges. One is sparsity, and two, cold start. New users don't have your previous data. And accuracy, we still want to increase accuracy of prediction and uncertainty. We should say that 10 new developments come from particularly maybe 5 or 6 PhD theses. And today I only quickly go through 1, 2, 3, 4, 5 of the 10 to deal with those issues in recommender systems. The first one, cold start problem. I'm a new user, you don't have my data. How can you give me personalized recommendations? So we use this social network and to identify more relationships between users. 2, tree similarity-based recommender system. This issue comes from real world. We need to think about when one item is a tree structure, how can we consider similarities between items or between users. Then we developed a series and algorithms and to compare the two trees similarity. Number 3, group recommender systems. Sometimes we generate recommendations not to one person, it's to a group. And the group of people may know each other, may not, may just online group. So we developed strategies and to think about how to have a group of users to generate a recommendation for group in large. Of course, 2 ways. One, we aggregate their ideas and generate a recommendation, or we generate a personalized recommendation but combine together. That is cross-domain recommender systems. You can consider this as transfer learning applications in recommender systems. Say we may have some domain don't have enough data to generate a recommendation, then a similar domain has a lot of data available. How can we transform knowledge from this system to help us to generate prediction of user behaviors or user preferences and to generate finally recommendations. The challenges here is the two domains may have a different feature space. And how to handle those issues, and we developed some algorithms, and this is published in attribute transcendental neural network. And the main ideas we need to transfer the knowledge learned in source domain and to help the prediction model in target domain. The final one is user interest driven recommender systems. Users, any single user or business user, their preferences may change. If you want to generate a recommendation to particular online users for property, then you need to quickly identify the changes of user preferences, then to generate accurate, personalized this recommendation through consider the interest drift. Decision support systems and these recommender systems are highly based on machine learning algorithms to deal with different types of issues and can be applied in different areas. As I mentioned, pricing, for example, and prediction, for example, and determine users' behaviors, and also generate customer relationship management, this improve customer relationship management, and also can be used in e-business, e-learning, e-commerce, and e-government. Those are the applications we have developed. What we have talked today, we talk about the data, and in the situation of big data. Then we talk about some challenges in data and how to use machine learning to deal with those challenges. Then we talk about how to use machine learning to help decision making and recommender systems. So the main idea is how machine learning can use data, generate models, knowledge to support decision making. My talk today covers quite a number of topics. I would like to use this opportunity to thank my team members, my students, postdocs, and all team members in my lab. And I would like to use the opportunity to have a promotion of our Center of Artificial Intelligence. Thank you.